Hello everyone. So this video is a continuation of the previous one for the suggested problems that is related to the last discussion session, and in this one I'm just going to go over the suggested problems from chapter 38. Okay, so the first one is problem number 1. The neutrons in a parallel beam, each having kinetic energy of 0.030 electron volts, are directed through two slits 0.60 mm apart. How far apart will the interference peaks be on screen that's 1 meter away? And they are giving us a hint. First, find wavelength of the neutron. Okay. So this is in fact just double slit interference experiment, Young's experiment, if you will, but with neutrons. So we have our usual setup. We have some screen that is 1 meter away, and we have a slit separation that is given to be 0.060. Let's make this call this D. So D is 0.060 millimeters, and I'm going to call this L. And this is of course going to create an interference pattern on the screen if we were shining light on this. Right? And they're asking for the separation between the two fringes. So that will be something like this. Let's call this H. This is the central maximum. Let's say this is the first order maximum, the separation between them, and we can determine the location of this first maximum. And if you just look at where it is with respect to the center, then we are going to find the separation between the fringes. However, in this case, we don't have light coming in, but instead neutrons. Right? And these neutrons have some energy. They are told that the energy of these neutrons is 0.030. So the kinetic energy is 0.030 electron volts. Right? Now, this kinetic energy corresponds to some momentum, and that momentum is going to correspond to some wavelength. So the relationship between the wavelength and the momentum is just de Broglie relation. So h divided by p gives the wavelength. So we need to express this momentum in terms of kinetic energy. Now, the kinetic energy is a half mv square. It's very safe to use non-relativistic formulas here, because this kinetic energy is much less than the rest energy of a neutron, which is about 940 mega electron volts. Right, so this is less than an electron volt, so it's very safe. So if I rewrite this, I can write this as 1 over 2m mv square. So this will be p square by 2m, and from this I can write P is equal to square root of twice mass times the kinetic energy. Okay? So this is going to be H over 2m Ke, the wavelength. And then we are going to find this H here. Let's say we have some angle theta, so that H is going to be L times tangent theta, right? But this is small angle, so I can approximate this as L times sine theta, and that sine theta is determined by the condition for the bright fringes, and that one is what we call the sine theta is equal to m lambda. Our m here is 1, so sine theta is just lambda over d. Okay. So this is going to be L lambda over d, and L is going to be given by this expression. So how would you find this? If you put everything together, actually you get L H divided by d square root of 2m Ke, like this. And let me erase this so I can show you how to calculate this, how to simplify the algebra a little bit. So H, the number you're seeking, is L by d, H over 2m Ke. Now it looks like you need to look up the value of H, the value of M, the value, convert this to perhaps joules and so on and so forth. But there is a simplification you can make, and that is you divide this by D, make this Hc. Hc's value you hopefully know by now. It's 1240 nanometers electron volt, and then this is going to become mc square Ke. Now I can write everything here in terms of electron volts, and this is an electron volt nanometers, so my answer is going to be nanometers, and these two I'm going to write in meters. So L was 1 meter, so this is 1. The silt separation was 0.060, so this is 0.06 times 10 to the minus 3. So Hc is 1240 divided by 2 to the mass of the proton. You can look this up. It's I think 936 mega electron volts. So this is 936 times 10 to the 6 electron volts, and the kinetic energy is given as 0.03. Right, so this is electron volts, this is also electron volts. You multiply them, you take the square root, the answer is going to come out in electron volts, which is going to cancel the electron volt here, and you're going to get your answer in nanometers, which I did. This comes to 275 nanometers. So, I mean, the question is actually over. At this point, you can just plug numbers in and find the answer, but there's a way to simplify the algebra, so I wanted to demonstrate that as well. This is certainly not necessary, but something I find useful. Okay, so the next question is problem 3. A proton is traveling with a speed of 7.56 plus or minus 0.012 times 10 to the 5 meters per second. With what maximum precision can its position be ascertained? Now this is an application of Heisenberg's uncertainty principle, and this is actually sort of a warm-up problem. It's a straightforward application of the basic formula, the uncertainty relationship between position and momentum, or sometimes a component of position and momentum, if you will. So this is problem 3. We are given, let me switch over here. So we are given the speed. The speed is not important, right? They are just asking. So it's just the uncertainty. So it's delta V is 0.012 times 10 to the 5 or minus 5. Is it 5? Yeah, minus 5 will be way too small. Meters per second, and they're asking what is delta x. Right, so let's call this x component of velocity. Now we have a relationship between delta x and delta px, and these have to exceed h divided by 2 pi, sometimes also called h bar, reduced Planck's constant. So we need to go from this to this. Now px is m times Vx, and from this it follows that delta Px is m times delta Vx. Right? So delta x is going to be larger or equal to h bar divided by delta Px, and this is actually equal to h bar divided by m times delta Vx. Right? So you need to again look things up. Again, if you want to simplify this, you could certainly do some manipulation to calculate these numbers. Okay, multiply both sides by c and so on and so forth. But just plugging numbers in is going to give you some number in meters, and I think it's going to be tiny. Did I calculate this? Actually, no. And you need to look up the mass of the proton, which is 1.67, 26 times 10 to minus 27 kilograms. All right, so as I said, this is a kind of straightforward application of this formula. So the next problem is perhaps more interesting application of uncertainty principle. So we have an electron in the n equals 2 state of hydrogen that remains there on average of 10 to the minus 8 seconds before jumping into n equals 1 state. Estimate the uncertainty in the energy of the n equals 2 state. What fraction of the transition energy is this? What is the wavelength width in nanometers of this line in the spectrum of hydrogen? Okay. So This is again an application of Heisenberg's uncertainty principle, but not of the uncertainty between position and momentum, but this time between lifetime and energy. Right, so this is problem 13, I think. Yeah. So let me turn this on. So we have an electron that goes from n equals 2 to n equals 1, and this is going to correspond to some transition energy. This is going to be 2 minus E1, and we can write this out. This is going to minus 13.6 electron volts divided by 2 squared minus 13.6 electron volts divided by 1 squared, which is just 1. Right? And this is 1/4, minus becomes 1. This is 1, so 1 minus 1/4 is 3/4. This is going to be 3/4 times 13.6 electron volts, right? So you can carry out the algebra. So we are looking at the uncertainty in the energy of this n equals 2 state, delta E. Now, as I said, there is a relationship between the lifetime and the energy uncertainty, and this is given by a very similar formula to moment and position relationship. This is delta E times delta T is larger than or equal to h over 2 pi. So this is given, this delta T is given, the lifetime is given to be 10 to minus 8 seconds, I think. That's a typical number, yeah. It's 10 to minus 8 seconds. And we are to find delta E. So we are going to say that delta E times delta T is approximately h over 2 pi. Right? Not only their product is larger than or equal to h over 2 pi, this is the limit, but we're going to say this is of the order of h over 2 pi. Right? So this is a very common way to estimate quantities using uncertainty principle. Why this is correct is a little bit beyond the scope of this course, but it comes from statistics and from Gaussian wave packets and things like that. It comes from the property of the wave packets and in the situations that we encounter. Okay, but once we do this, we can write that delta E is h over 2 pi divided by delta T, and this delta T we can actually plug in and we can find some delta E. Right? Yeah. So for part B, they're asking what fraction of the transition energy is this. So we calculate the transition energy here. So if we get this number in electron volts, then we can write this. We can calculate this in electron volts. Then we can calculate the ratio very easily. And here, yeah, what will this be? So again, I will write this as h times c by 2 pi divided by delta t times c, and these are things that I actually know. So 1240 divided by 2 times 355 by 1113 by delta t is 10 to the minus 8 times c is 3 times 10 to the 8, but I want to write this in nanometers, so this is going to be 10 to the 9. Okay, so these 10 to the minus 8 cancel this 10 to the 8. These are of order, let's say, unity. This is like 100 or so, but in the denominator we have 10 to the 9. So this is going to be a very small number in electron volts. So and since this is like of order 10 electron volts or so, this is going to be a tiny fraction. Right? Like it's 1 part in a billion or so. So I mean, you need to carry out the calculation for the exact answer, but this is going to be something small. Right. So I'm not going to calculate this in detail because this is not really very instructive. Now part C is what is the wavelength and width in nanometers of this line in the spectrum of hydrogen. So let me erase this. This is something we can remember. So we want to calculate the lambda and the uncertainty in lambda. So lambda energy is h times f, so this is h times c over lambda, so therefore your lambda is going to be h over e, right? This is easy enough. If you calculate your energy in electron volts, which we did, it was 3/4 times 13.6 electron volts. You can calculate this in nanometers very easily, right? But then, is the delta lambda equal to hc over delta E, right? And hopefully we are going to go over this in the discussion session, but the answer is no, right? Given this relationship, you can't go to this. So given this relationship, P equals mv, you can go to delta P equals m times delta V, but this doesn't follow from that, right? This is wrong. Now why? What is the difference? Here, the relationship between momentum and velocity is linear. The relationship between wavelength and energy is nonlinear, right? They're inversely proportional to each other. It could be another nonlinear relationship. It could be it's proportional to the square. It could be it's proportional to sine of this or something like that. But this substitution will work only for linear relationship. For anything nonlinear, you need to do something different. And the easiest thing to get the uncertainty relationship for a nonlinear relationship between variables is to take derivatives of this, right? So you take this, you take derivative of both sides. So the left hand side becomes d lambda, the right hand side becomes minus hc by e square dE, right? So this is just taking derivative of both sides, and then instead of the derivatives, you just substitute uncertainties. There is, of course, a more rigorous way to calculate this, but I'm not going to go into this. This is, I think, simple enough, because this is pretty much the only nonlinear relationship we are going to be dealing with. So if you have an inverse relationship between two variables, their uncertainties are related this way. Okay? And now once you have this formula, since you have delta E and since you have E, you can easily calculate the uncertainty in wavelength using this formula. Now, there is one way to see that this is incorrect, right? So intuitively, you would expect that because these two are related to each other, and there is some uncertainty in energy, there should be some uncertainty in wavelength as well. However, if you look at this formula, as you increase the uncertainty in energy, the uncertainty in wavelength actually decreases. So this is not something, this doesn't make sense, right? This is not something you would expect. Whereas if you look here, as you increase the uncertainty in energy, the uncertainty in lambda also increases, but it's not linear, so it also depends on at what energy you are. So this is not intuitive. You can't intuitively tell what this factor is going to be, but this relationship is kind of intuitive. They should, to first order, as long as the energy is not changing from one situation to the other, they should be just directly proportional to each other. Okay, so let's look at the last one. I'm not going to solve the last problem, which I marked as optional, but I want to discuss what's going on here. So we have a double slit experiment made by electrons or photons, it doesn't really matter. And this is an application of uncertainty principle. So let's say that we suppose that we use indicators to determine which slit the electron went through. Right? So for that, to tell which slit it went through, you need to be able to determine its vertical position, or the vertical component of its position, within an uncertainty of half the slit separation. That's the d over 2 in this case. Now, if you do that, if you determine it with this certainty, then it's going to introduce a vertical component of momentum. Right? And that vertical component of momentum, there's going to be an uncertainty in the vertical component of momentum, and consequently, this is going to change where this particle is going to arrive on the screen. Right? If it picks up a vertical component of momentum, then it can go slightly higher or slightly lower when it arrives on the screen. And it turns out that's enough so that uncertainty, this uncertainty momentum in the vertical direction corresponds to the uncertainty in the position on the screen, and that uncertainty is equal to the separation between the fringes, or it's on the order of the separation between the fringes, and that is enough to erase this interference pattern. That's the idea. Okay? So this is discussed in Feynman's lectures on physics, volume 3. So I recommend that that you look at this. But this is also something discussed in many other books. I think one resource will be the Berkeley Physics course, Quantum Mechanics volume, which is actually an excellent volume if you want to teach yourself quantum mechanics. That is one of the books I would recommend, and it is also translated into Turkish actually. And well, not during the pandemic, but after the pandemic, if you stop by my office, I'll be happy to lend you my copy. Okay, that's all I want to say. Thank you.